I'm waiting for the clock to turn to 15. There we go. All right. Well, welcome to Spring 2022-23 Senior Design Presentations. I'm John Taché, and I'm the coordinator of our Senior Design program. It's my pleasure to welcome you to this presentation, the day of presentations. We've got students here, faculty here, industry sponsors, and we've got folks online. Welcome to you too, friends and family that are interested in what the students are doing. This is the culmination of our capstone program, and we'll have 12 presentations today, starting off with this one, which is LEVIS, and they will tell you all about it. If you are a faculty member or an industry sponsor, hopefully you've got a or industry partner, a blue form for filling out a review sheet. If you're a senior design student, you need a white form to do an evaluation as well. Let me pray for them and we will get started. Lord, thank you for this very nice day, this culmination of the semester. It's a beautiful day outside for all the people in the room and for these students here who are ready to present what they have learned this semester, their accomplishments, successes, and trials as well that you've been working in their lives. Would you bless them in their presentation, our technology? We're very grateful. In Jesus' name, amen. Savannah.
Oh, thank you. Good morning, everyone. We are LEVIS, the LeTourneau Engineering Vital Imaging System, and welcome to our final presentation. My name is Savannah Orton. I am this year's team lead, and our faculty sponsor is Dr. Junwon Kim. We have two sub-teams, the software team and hardware team, and leading our software team is Ian Crochet, followed by Demeji Apo-Okagi, Evan Kowal, Samson Segovia, and Francis Ko. For our hardware team, we have Julian Lee, who is our hardware team lead, followed by Ashley DeCock, Aaron O'Brien, and Morgan Nix. To begin today's presentation, I will first begin by introducing respiratory rate. Respiratory rate is a vital sign that signifies the movement of air into and out of the lungs. This vital sign is known to be one of the most inaccurately measured vital signs, as it is often omitted and not recorded entirely. This observation can be problematic considering that fluctuations in respiratory rate range are often observed as an early indicator of illness and cardiac arrest. The current solution to measuring and monitoring respiratory rate is through a manual counting regimen where a hospital staff or healthcare worker will count the chest deviations of a patient's chest in order to determine the breaths per minute. However, this is not representative of how hospital staff are trained to measure respiratory rate in the field due to the tedious nature of this measurement. Therefore, a device was proposed to non-invasively measure respiratory rate as a way to lessen the burden of this tedious measurement on healthcare workers. Therefore, the objective of this project was to determine a method to measure and monitor respiratory rate non-invasively and accurately for a telehealth setting. This project began a few years ago with Breathe, the first team that fabricated a respiratory rate monitoring device for an ER setting. As shown on the left, their device was able to attach to an existing IV pulse stand and utilized a thermal camera for thermal analysis. However, their prototype possessed various cords and sharp edges, which may pose as a safety hazard in a true ER setting, even though they were able to produce a respiratory rate measurement. Additionally, their prototype had to be placed in a very close proximity to a patient's face, which is not ideal for a true measurement in an ER setting. This project continued on another year through the LEVI team, where they chose to fabricate a device suited for a hospital setting. As shown on the right, their device was modified to have a craning arm feature that allowed for easy movement of the cameras to the exact location of the patient's face. In addition, to increase the depth of field of the measurement, they incorporated an RGB camera to integrate facial recognition along with the thermal analysis component. This team also pitched a business plan to the TCU Values and Ventures business competition, where they received helpful feedback from a variety of industry professionals, which led us to help develop the scope for this coming project. And now to discuss the constraints, deliverables, and finances is Aaron.
So we had three main categories of constraints for this project. In terms of cost, we wanted it to be affordable for the people who need it. For measurements, we needed it to work at a distance of 1 to 2 feet at a 30-second time interval. And for ease of use, it needed to have a simple interface, but be portable, contained in a single unit, and be completely non-invasive. Our deliverables were a functioning respiratory rate device that had an accuracy measurement of above 58%, a device interface with a cellular app, and a research paper submittal to a conference. In terms of expenses, our budget estimation was about $3,100. We came in at about $2,900, so about $200 under budget. The breakdown divides into about $370 for hardware, $300 for electronics, $2,200 for conference submittals and travel, and about $20 of shipping. And now Demeji will present to you our project timeline.
In order to understand the steps necessary to take to complete the project on schedule, we created a timeline overview. We divided this into 4 phases. Phase 1 consisted of background research. We submitted our conference abstracts for the various conferences we wanted to attend. We made a mobile app proof of concept, and we selected our initial parts. In phase 2, we made performance improvements and integrated the UI and our software with our device. We developed our mobile application, finalized our components, and we made a 3D model of our device. In phase 3, which took place in the spring semester 2023, we debugged our program, we completed our surface finishing, we assembled and tested the device, and we finalized the whole device. Phase 4, which is the final phase, consisted of attending our conferences, our final presentation, and final documentation. And now Evan will talk about our current model.
Based on the work of previous years, our design constraints, and our project timeline, we have developed the current design. Our respiratory rate device has been modified for work in a telehealth setting and is equipped with both thermal imaging and facial recognition software. Our device stands approximately 15 centimeters tall and is 12 centimeters in both width and depth. It interfaces with a mobile application for ease of use and display with patients, and it is set to a 30-second time interval for measurements. It is estimated that our device will cost approximately $330 per unit. A brief comparison to last year's device, the Levi team created a device that positioned its cameras vertically and captured images independently of each other. In order to rectify the image displacement from this orientation, they based their image displacement around a manually set matrix. Furthermore, their device was composed of multiple units, and was battery powered. This caused the power system to be slightly unreliable and the device itself to be overly cumbersome. The following changes have been made this year. We have positioned our cameras horizontally in relation to each other, and they are now able to capture images simultaneously. Our image rectification has been fixed by using the bounds for each camera. We have condensed our unit, as you can see, into our device, as you can see, into a singular unit that is interfaced with the cellular application. And we have also added a wall outlet connection to provide steady and reliable power. I will now hand it off to Ashley, who will present our research for this semester.
In order to test the accuracy of our device, we entered into a phase of data collection. We first had to obtain approval from the university's Institute Review Board. And once we were approved, we then tested on 12 different subjects and had 10 trials for each subject. We tested our device against the manual counts, which is counting the chest deviations of the subject against our device. And we verified that manual count with a heart rate signal, which was obtained through a BioPack system, which is shown on the right, and our subject was attached via electrodes. And on the left, you can see our subject seated in front of our device, which is about 45 centimeters away, and the device angled at 30 degrees. And we kept that consistent between our trials to ensure we were obtaining correct values. This is a sample of what our thermal camera sees. On the left, you can see the subject is inspiring or breathing in, as there are cooler toned colors around the nose, which represent cooler temperatures. And on the right, you can see the subject is expiring or breathing out, which you can see by there are warmer toned colors or higher temperatures. After data collection, we then processed that data. We used an algorithm that was able to detect the number of breaths during a recording duration. We implemented a third order low pass Butterworth filter, and which would amplify the low values and minimize the high values. We also used thresholds to detect the variation as the signal passed through. And that was how we obtained our respiratory rate, as it was a cyclic pattern. To come up with a result, we had to come up with an accuracy equation, and we took the number of usable trials that were within plus or minus 2 breaths of the manual counts, and we divided that by the total number of trials that were usable, and we multiplied that by 100. We were able to obtain an accuracy score of 64.9%. However, there is no common reference or standard for respiratory rate measurements. So we turned to research, and we found that a study that was done in a hospital setting utilized a tolerance of plus or minus 2 breaths. So we then implemented that into our study. And now Julian will talk more about our team's accomplishments.
The hardware accomplishments include the following. We were able to create a full model of our device in SolidWorks, and we were able to document this device with engineering drawings for manufacturing purposes. We were also able to 3D print the device, complete a sanding process and painting process for our final assembly. In addition, the hardware team designed and built a display to be displayed in the engineering building hallway. We also completed a non-provisional patent application, which was filed on April 15th. This patent application, should it be approved, will exclude others from using, creating, or selling similar technology. The software team was able to complete several things this semester. They were able to have the cameras simultaneously record data, which was a big improvement from last year's, where the cameras had to independently capture images. The software team is also able to successfully create a cellular app, which operates the device, receives data, and can display this data. In the cellular app, the user can observe their respiratory rate and compare this number to the normal range for respiratory rate. As we said, we had a deliverable to create a product with a higher accuracy than 58%. We were able to do this, and this number was the accuracy from a study conducted by UT Southwestern Medical Center in 2019. This study showed that these trained patient care assistants could only, when measuring respiratory rate, they measured an accurate number about 58% of the time. I would also like to highlight our research conference accomplishments. This year, our team was able to complete the deliverable of a conference paper submission at SPIE, Smart Structures and Non-Destructive Evaluation Conference in Long Beach, California. For this conference, we were able to submit a manuscript, and this will be published in SPIE's conference paper. LEVIS also competed in the IEEE Region 5 student poster competition. In the East area of Region 5, Levi's placed first in the poster competition. Because of this, Savannah Orton was invited out to Denver, Colorado to represent the Levi's team, where she placed first in an oral presentation competition. And now Samson will provide a conclusion of this year's work.
In conclusion, we've met our deliverables by creating a device that can measure respiratory rate with an accuracy above 58%, and our device can interface with a cell phone app. Our team has also written and submitted a manuscript that will be published by SPIE. Our device has the potential to be in the future to be in numerous areas in the medical field. Nurses or other medical staff could attend to other tasks while our device records a respiratory rate. Our device is a non-invasive measurement, which means that there is not a necessity for physical contact. This will reduce medical waste. And further improvements of the data processing algorithm and upgrading components such as the thermal camera may yield a higher accuracy. Now Ian will provide a brief demo.
Now for the rest of the presentation, I'll help out with presenting the demo. So let's get started, shall we? We're not going to have my mic around here. A little bit loud. So can you all hear me? All right, perfect. So within this is kind of the ideal setting for the overall product. To the left of me, I have my phone, and to the right is the overall Levi device. Ideally, we have our own UI implemented that basically is able to connect with the phone. Basically, no. Thank you so much, sir. Can y'all hear me now? Oh, perfect. Thank you so much. All right. So just as I was saying, we have the overall product right here, where to the left of you is your overall phone that has the app that will be connected to your device. So ideally, when I press, let me check just for a second for settings as I reconnect the device. When I record the data, it should be able to initialize the RGB camera. And from there, I can do a 30-second breathing. And as this is going, it's able to record my face. So I'll just kind of breathe for a second. So the Levi was able to perform a live video feed recording, and usually around 5 minutes, it takes a while to do some post-processing. And from there, I was able to get 10 breaths per minute. And from there, lastly, Savannah will then present us with the acknowledgements. Oh, yes. Oh, yeah, sorry. Check it out. 10 breaths per minute.
And to conclude today's presentation, I would like to acknowledge lots of people that have helped contribute and support us throughout this process. First, Dr. Liu, who is a physician at the VA Medical Hospital in Tucson, Arizona. He is a LeTourneau alumni that first proposed the idea of this device, so I'd like to thank him for this idea. As well, I would like to thank and acknowledge the previous teams that came before us, Breathe and Levi, the LeTourneau Engineering Venture Initiative. As well, I'd like to thank our faculty advisor, Dr. Jun-Won Kim, and the volunteers that have aided in this process, Francis Ko and Esther Kim. And lastly, our patent agent, Dr. Gary DeBoer, who has been a tremendous help in helping us learn how to file a patent application. Thank you all for attending our presentation today.
All right, we have some time for questions from the audience. If you're online, please type your question into the chat and we'll get to you in a few minutes. But ready for anybody who has a question over here?
Again, congratulations on the presentation, and also with the IEEE and the SPIE presentations, because that's awesome how we're representing LeTourneau and all of that, getting the word out, and especially a product that's patentable and it could be out in the market representing the university very well. So congratulations. Question I had was on the camera and the limitations on the camera, because even on the previous year, there was always the concern about you could only stay within so many feet and you cannot stay away from that, like up to 5, I think it was 5 feet, anything more than 5 feet, you would not be able to pick it up. And anything closer than 6 inches, you would not be able to pick it up. So has that changed? What's the update on the camera, and why do you have that limitation?
Well, thank you at first for the wonderful comments about our presentation. We've been so excited that we've been able to represent the university well. As far as the cameras, last year's project, they had focused on increasing the depth of field, which was helpful through the facial recognition. We decided, because of the telehealth setting that we're tailoring our device toward, that it wasn't as necessary to perform a measurement as such a great distance away. We're imagining this device to be used in a similar setting where a patient is monitoring their own respiratory rate at home or in tandem with a physician over a Zoom call. So with that said, we chose to maintain a closer measurement range as a way to increase accuracy, because we learned from last year's team that if you're at so far of a distance away, it may yield a lower accuracy result. As well, our team has been able to successfully implement the facial recognition by allowing the cameras to work in tandem, which has been very helpful considering that the previous years had an issue with facial recognition being lost. But because now the cameras are able to work simultaneously, we're able to maintain facial recognition underneath the area of the nose at a greater rate, which has helped with accuracy. As far as the limitations of this camera, we believe it primarily to be due to the lower resolution of these cameras. We thought it was important to have a device that is fairly accessible and inexpensive for the at-home user, which is why we're using cameras that are of lower resolution. But if we were able to have an increased budget or upgrade the prototype to one that includes higher resolution cameras, we may be able to see better accuracy at a greater distance away and limit these limitations that we're seeing. Does that answer your question? Yeah, thank you.
I echo Murray, good job on the presentation and the product. What do you have with regards to alarming, either for measurement error or unhealthy results?
To answer this question, I'll refer to my software team.
Yes, all right. I'll be happy to answer that. So I did a lot with exception handling. So a lot of the times with working on Levi, there was a lot of segmentation faults because since we're considering doing live video feed in correspondence with both the RGB and the thermal camera in coordinates with each other, there's a lot of issues with kind of boundaries because you're dealing with two different fields of view intersecting with each other. So in order to do that, I created like a boundary limit to where if the like nose coordinates are like outside the pixel range, it'll stop the data from transferring. And I'll let it has like a text on the top right saying either it's saying out of bounds or frame rate is lost. So anything that either the rest, like the facial recognition doesn't recognize anything, or if it's out of bounds to where it will cause errors within the thermal camera, it'll instantly close out the window and notify the phone with an error, because the phone operates in two processes. It either listens for errors or it listens for breath. So during recording, it listens for any errors that are sent by the device, and it's able to then like close the recording and say, oh, would you like to restart it? Does that answer your question?
That's part of the question. That's in terms of measurement error.
Right.
What about having unhealthy results?
Unhealthy results. For the most part, we're mostly focusing on getting like an accuracy of breaths. So that over time, if we wanted to work on this in the future, we would like have something on the phone that would like recognize that. Now we're kind of just measuring if it's able to record like breaths overall.
Okay, so there's nothing about breath quality or
No, sir.
evaluation?
No.
Okay.
Thanks. Hope that helps.
Anybody else have a question? This is legal to have a volunteer to ask a question.
Well, first off, I just want to say it's a really great presentation from the bottom of my heart, and the device looks good. And then my question, since I don't see a certain general here, I was just wondering what y'all thought about as a team, how you grew, especially as 80% of you are now in your last semester at LeTourneau University, and just what your thoughts about that and reflecting on your capstone project.
Yeah, thank you, Francis, for that question. Our team has had a lot of time to reflect on this last semester as students and what God has been teaching us through this time. One of the biggest lessons that I feel as a team we've learned is how to be completely dependent on the Lord. There's been a lot of challenges in this project. There's been a lot of late nights, early presentations at conferences, and instances where our own strength was not enough to allow us to succeed. And this has taught us tremendously about the power of prayer and dependency on the Spirit to give us strength, because we wouldn't really be here having a successful product without the Lord. He is our strength and has allowed us to accomplish so much more than we could have expected throughout this process. Thank you.
Thanks for your testimony, Savannah. Who else has a question?
What are some notes you have for any future years on the projects, or do you plan on keeping this project running in future years?
At the moment, I do not believe that this project will be continuing on another year. However, if there ever was a resurfacing of this project, it may be valuable for a team to assess the various parameters we have in our data processing algorithm, as much of those were determined arbitrarily and were tested upon to reach the 58% accuracy, such as the filter order or the number of points that are calculated before a new average is assessed. Some of these parameters could be further researched upon in order to see if there's an improvement in the algorithm, as well. If there is a potential industry sponsor for this project, we may be able to upgrade the current components of the device to utilize a higher resolution camera. There was a graduate student a few years ago who worked on a similar project that utilized a higher resolution camera and received very good accuracy in his measurements. So we believe that might translate well to this project if we're able to do so in the future. Thank you.
Well, first, congratulations. My question goes through to when you were taking the measurement a few minutes ago, the illumination, you have light in his face. And I would like to know if that is an issue in taking measurements, and also the environment temperature. Like some hospitals will be very cold and clinics probably will be in an area that are a little bit hot. So did you consider that into your design?
The reason why we have the light illuminating the subject in this setting is because of the lighting that we're not very familiar with. The lamp allows us to have a clear illumination of the face without worrying about different shadows. That was due to a concern that maybe facial recognition might not work as properly if we're not having a clear illumination of the face. As far as a hospital setting, I do not believe that to be a huge issue, even if the environment is significantly colder, because our algorithm detects a very small area underneath the patient's nose and will capture what the temperature is as they are breathing in and out. So because that area is so small and so close to their nasal region, I don't believe that that would affect the temperature of what's going on internally. Thank you.
So we have some technical difficulties and are not able to accept questions for this session online. But because one of the alums has Dr. Kim's cell phone, I can ask this question. Can you ask them what technologies and software they used for developing the mobile app?
I'll refer this also to the software team.
Just to ask, is this specifically just for the mobile app or is it just for the general? Okay. So for the mobile app, we use Flutter for basically developing the overall mobile app. A lot of the communication between the device and the phone is developed through MQTT, is more of a low energy based Internet of Things technology that's able to it's almost like Bluetooth, but it's much more faster to send like data in. Along with that, the UI for the Levi is run through Kivy, is more of a Python-based graphical user interface. But majority of the code for initializing the cameras is done with C++ and Python. And I hope that answers your question.
So you mentioned that you had filed a provisional patent application. Are there any plans to, I guess, market that or make use of that in any way, or is that just to have a patent for it?
Well, the team last year, they were the first to initiate the provisional patent application. And the application has a full year duration where you're able to complete that application fully before submitting it to the patent office. So because we had that foundation of the patent application last year, we chose to upgrade the current application to include the new design as well as implement better descriptions and drawings for the previous year's team. At the moment, there are no plans on manufacturing this device. However, if there's another team in the future or a business team from the university that is potentially willing to market this device, that may come up then, but there's no plans at the moment. Thanks.
I'm by no means an engineer. I'm a nursing major here at LeTourneau. So disclaimer, I find this very interesting, but I have a few questions. Would y'all see this like going into the hospital setting?
At the moment, the technology is the same across the majority of the prototypes we've had. So I believe it is possible to have it in a hospital setting, but of course, in order to be matriculated in, we would need to undergo various FDA testing and a lot of different regulations to ensure that it is safe for patients to be around. As well, the current accuracy would probably need to be improved at a greater level than what it is currently displaying. We chose to have the device tailored for the telehealth market based off of industry professionals' feedback. They thought that the hospital ER setting was very saturated already with medical equipment and that having a device more suited for the new and emerging telehealth market may be an easier fit for especially a smaller company or business that we have. However, I believe the technology is there and we have the rights to exclude others from producing or manufacturing this product. If we're able to invest more time and research into this, I believe that it would be able to be useful in a setting as you're describing and maybe help nurses like yourself to attend to other tasks while we can provide an accurate assessment of their respiratory rate.
Yes, because I 110% agree that respiratory rate is not properly recorded, especially in the ER setting when things are going at 100 miles per hour. So, and then I know he asked a question earlier, but again, for the light on the face, do you always have to have proper illumination on the face, or could the prototype be involved to where that's not a necessity, especially in the hospital setting? Say for certain patients, you can't have illumination on them because that stimulates their brain, can put them into a worse situation.
Right. We chose to have the light strictly in this instance for demo purposes so we can ensure a good measurement, but we have tested instances where we haven't used the light and still have received a good measurement. So I don't believe that the light is a requirement, especially if we can have the ability to assess the patient that will be using it. If the light could potentially stimulate negatively in a way, we don't have to use the light. But
And just out of curiosity, have y'all ever tried to see what it does if, say, like some patients, they mouth breathe, they don't breathe through their nose? Have y'all like tested out of curiosity to see if y'all's prototype even can record that?
Well, I know that it wouldn't be able to record because the nasal region is the only region of the face where the temperature coordinates are being calculated from. That would add some complexity, as you mentioned, if they were a mouth breather. However, due to just the scope of this project and the constraints that we have, we chose to focus on the nasal region specifically. Yeah, thank you for your questions.
Like, I'm pretty sure it's almost time, but could you turn on to the, the video clip that people can see that?
Sure. We have a recorded demonstration as well for those of you that are online. There's currently no sound, but as the user pressed the record new data button, the device is able to display what the RGB camera is viewing, and the patient is able to see the pixels underneath their nose where the thermal coordinates are being collected from. And after the duration of recording, there is a small time delay where the device will calculate the respiratory rate and send it over to the phone application. And we can see that they had 14 breaths per minute in this run.
Thank you very much. Very impressive.
Yeah.
We'll have about a 10-minute break, and next up will be the Rep 23 team. Thank you, guys.